Well, today we're going to discuss the central concept of general relativity, which is called geodesics. Geodesics. Geodesics in curved space-time is equivalent to straight line in Euclidean space. In flat space, what is called straight line. In curved space, that thing is called geodesic. So, obviously, there are two properties. One is it is the shortest distance between 2 points. Another is the tangent vector to the geodesic points in the same direction. These two properties are there. Say, what is a point? Whenever we define a point, we write x vector. This is a point. Now, what is a curve? When x moves and x traces out a certain line, as another parameter is varied, then it traces out a curve. Say, in ordinary, I am a particle. I trace out a curve. If time does not elapse, if time does not vary, can I move and trace out a curve? No. So there should be a parameter which changes, and that change entails the change gives change in x. So there should be a parameter. That parameter we take as sigma. Sigma. Whatever sigma is, actually we should discuss later on. Now take a small infinitesimal displacement dx. You can write it dx by d sigma multiplied by d sigma. Now d sigma is a scalar. This is a vector. So dx by d sigma should be a vector. Dx by d sigma should be a vector. The components of dx by d sigma are called x dot nu. Dx by d sigma components are x dot nu. Dot we shall use differentiation for differentiation with respect to sigma. We shall use dot for differentiation with respect to sigma. So dx by d sigma has components x dot mu dx mu by d sigma in component form. That was in compact form. The whole was there, dx by d sigma. Now the components are there. Okay. I have a curve x of sigma. I have a curve x of sigma. How long such a curve? First of all, come to infinitesimal length. Actually, we know the interval or the squared length is given by ds square is equals g mu nu ds mu dx nu. ds square is found by g mu nu dx nu dx nu. ds is what? Square. Square root of this is the ds. And what is the length? Total length? Total length is s. But between what points? Say the points are sigma 1 and sigma 2. The parameter and parameter are sigma 1 and sigma 2. Between these 2 points, the total length of the curve is x, s, and we shall find it by integrating ds. So I have written the ds term. And this is called sigma 1 sigma 2 integration square root of L d sigma. While L x mu x dot mu given by g mu nu x dot mu x dot mu. Come here. Had a square root. If I multiply by d sigma beyond the square root and within the square root I divide by d sigma, then the expression will same. I am multiplying by d sigma after the square root and dividing within the square root by d sigma squares. The expression will same. Now dHb by d sigma is h dot nu, dHd by d sigma is h dot nu, and then d sigma. So what is L? L is g mu nu x dot nu x dot nu. So square root L here d sigma. So this is the length S. Now, if this S has to represent a geodesic, it should be the shortest. So we call it extrema, extremal value. For extremal value, if you make a distortion, if you do a distortion, even then distortion will not change the length. There is a variational principle in classical mechanics. The variational mechanics gives Euler-Lagrange equation. Here also we shall find the Euler-Lagrange equation. Because we have the L Lagrangian, we shall get Euler-Lagrange equation. What is the point? The point is, if the curve x of sigma is distorted, if x of sigma is distorted by epsilon chi, then we get the curve, then we get the curve x plus epsilon chi. This is the distorted curve. What is that? Say say this is x of sigma. Here is sigma 1, here is sigma 2. This is x of sigma. Now you want to distort it. How do you distort that? So you distorted it. This curve is x plus epsilon chi. This curve. This curve is x of sigma. The distorted curve is x plus epsilon chi. Here, epsilon measures how far is the distortion, and chi defines how it is distorted. Chi gives the quality of the distortion, epsilon gives the quantity of the distortion. Okay. Now, if after this distortion the curve is geodesic, if the curve is geodesic, after this distortion the total length will remain same. Say S of epsilon is the distorted curve. S function of epsilon is the distorted curve. For x of sigma to be geodesic, ds by d epsilon, epsilon equals 0 should be 0. It is the requirement of variational principle. It is the requirement of variational principle. If you differentiate S with respect to the variation, and after differentiation take epsilon equals 0, that means there is the distortion, then it should be equal to 0. Now we shall do the mechanics. How we will do that? First of all, S function of epsilon is integration sigma 1 to sigma 2 square root of third bracket L function of x plus epsilon chi factor comma x dot plus epsilon chi factor dot third bracket sets this sigma. I have done nothing. We have done nothing. S was square root of L d sigma. Now I have explicitly written what L is function of. This is the same expression beforehand we have written. Now we have explicitly shown what L is function of. Now L is function of x plus epsilon chi and also of its derivative. So the second term comes. Okay. Now do the differentiation of this ds epsilon by d epsilon. What? You don't have to think about this. What is this? Root over of L. If you differentiate within the bracket, you can do that. L to the power half differentiation will give you half L to the power half minus 1 L to the minus half, that means here will be root over L. Okay. Next, you have differentiated this with respect to arbitrary something sigma, but L is function of x dot chi dot. That should be reflected here. That should be reflected. So what is that? For this is del L by del for this x dot mu chi dot mu in component form. In component form, L is function of this. Its components are what? X dot mu. Its components are what? Chi dot mu. So this is differentiation of L with respect to x dot mu. Why? Because L is function of this. Then remains you have to differentiate with respect to epsilon. If you differentiate with respect to epsilon, here it will give 0 because there is no epsilon here. Here is epsilon cancels. You will get only chi dot. So I have written chi dot. This is the differentiation of chi dot q. This is the lone term chi dot q because differentiation eliminated the term epsilon only. Plus of first term del L by del x mu chi mu this sigma. So this is the differentiation. Now this can be written as half integration sigma 1 to sigma 2 d sigma minus square root of L del L by del x dot mu plus 1 by square root of L del L by del x mu chi mu d sigma. How can you write this? How can you write this? So to find this, we shall do the detailed calculation, but not so detailed. Little bit of details. First of all, come to here. How this is done? ds by d epsilon equals 0 is given by sigma 1 to sigma 2 d epsilon square root of L function of x plus epsilon chi x dot plus epsilon chi dot d sigma. Right? Differentiate, you will get sigma 1 to sigma 2 1 by 2 square root of L. Before and I have said this. The differentiation explicitly is del L by del the second term first, x dot plus epsilon chi dot. Now this should be differentiated with respect to epsilon because the differentiation is with respect to epsilon. So you write del x dot plus epsilon chi dot by del epsilon. Plus of come to this point, del L by del x plus epsilon chi vector del x plus epsilon chi vector divided by del epsilon gone the sigma. Now what about this? Epsilon has to be 0. So right here epsilon equals. In this term, if you write epsilon 0, there remains only x dot. So the term will be sigma 1 to sigma 2 1 by 2 square root of L del L by del x dot on this term. Here, when you differentiate with respect to epsilon, this term gives 0 because it doesn't have epsilon. Here epsilon already cancels out. What remains? Chi dot mu. In component form, this is what? In component form, chi dot. Okay, next term. Plus here del L by del x cube. Right? Epsilon 0, second term 0, x in component form, x cube. Here, when you differentiate x, you get 0. Here, epsilon cancels out, you get only chi. This is one. Now, how do you go whatever I have written beforehand? Note that sigma 1 to sigma 2 1 by square root of L del L by del x dot mu chi dot mu this sigma is equals sigma 1 to sigma 2 d sigma minus 1 by square root of L del L by del x dot mu chi mu d sigma. Why? Because write sigma 1 to sigma 2 d sigma 1 by square root of L del L by del x dot mu chi mu d sigma is equals what? This sigma cancels. Remains d of this thing. If you integrate, you will get 1 by square root of L del L by del x dot mu chi mu epsilon equal to 0.
Chi dot.
No chi dot. D of this only I will get this. is equals to 0. Why? The n points has chi equals 0. No distortion at the endpoints. No distortions at the endpoints. So chi itself is 0 at the endpoints. Here I have sigma 1, sigma 2. At sigma 2 it is 0, at sigma 1 it is 0. So this expression is 0. So come to this point here, I shall employ this thing, not this thing. I shall employ this thing. Come to here. Take this as a single term. Take this as a single term. You get integration sigma 1 to sigma 2, 1 by square root of L, del L by del x dot mu. Second term, you differentiate. D chi mu by d sigma plus first term you have not differentiated, now differentiate this d sigma 1 by square root of L then L by del x dot mu chi mu d sigma d sigma is equals 0. I can write chi mu outside. So I have 1 by square root of del x dot mu del by del sigma by del chi mu by del sigma d sigma 1 by d sigma 1 by square root of del by del x dot mu chi mu d sigma 0. Now you interchange the terms. If you interchange the side, you will get sigma 1 to sigma 2, 1 by square root of L, del L by del x dot mu, del chi mu by d sigma, d chi mu by d sigma, this term. Is equals sigma 1 to sigma 2 d sigma minus 1 by square root of L del L by del x dot mu chi mu d sigma. Right? Only just side change. These two terms becomes 0, so this term becomes minus. And what we have written beforehand, what was that? What we have written? We have written in the beforehand that ds of sigma by d epsilon equals half integration sigma 1 to sigma 2 d sigma minus 1 by square root of L. No, we have not written this yet. We have written sigma 1 to sigma 2, 1 by 2 square root of L. You remember this now. Del L by del x mu dot mu chi dot mu plus del L by del x mu chi mu d sigma. We have written this. Now, what is the first term? The first term is 1 by square root of L del L by del x dot mu. What is this? Del L by del chi mu by d sigma, nothing but chi dot mu d sigma. So this term is equal to this term means minus with minus. So we shall get half sigma 1 to sigma 2 d sigma, this term, the first term is substituted by this term minus sign. d sigma minus 1 by square root of L del L by del x term mu plus the second term remains same, 1 by square root of L, 1 by square root of L del L by del x mu, finish chi mu d sigma. This has to be 0 for arbitrary chi. For arbitrary distortion, this has to be 0. So the integrand should be 0. Integrand should be 0. So we get what? We get d sigma 1 by square root of L del L by del x mu. It is minus sign. So minus sign give here. Minus 1 by square root of L del L by del x mu equal to mu equals 1. The how many coordinates are there? It depends on that. So this form is similar to the Lagrange equation. Similar to the Lagrange equation. Now only thing is sigma. Now sigma can be tau, proper time, or s. What is s? The interval. We define interval by s. So s is the interval. If you use tau, L becomes c square. If you use s, L becomes 1. So tau, s, these are called affine parameters. Tau and s are called affine parameters. You know why? Because whenever L is a constant, then we have the equation like L is constant, I can take out this outside. Then 1 by root L can be cancelled. I'll get for affine parameters the equation is d sigma del L by del x mu minus del L by del x mu equals 0. Exactly the Euler form. Exactly Euler form equation is obtained whenever your parameter is tau or s, proper time or interval. In that case, L is c square once, L is 1. Whatever it is, it's constant. So you can take this out, that cancels out of that, you get the Euler form. Whenever the equation is Euler form, the parameters are called affine parameters. So this is the equation for geodesic. If you want to find out the geodesic, solve the Lagrange equation, Euler-Lagrange equation of geodesic. This is called the Euler-Lagrange equation of geodesic. If you want to find geodesic, solve this. We shall come across this for this equation many times in future in this course. So to do this part. Thank you.